Welcome to Melius Mentorship, episode 1 of Chemistry 12. Today we're going to be talking about redox and redox titrations, as well as oxidation reduction reactions and electrochemical cells. So let's first start with what is a redox reaction. A redox reaction is a reaction through which reduction and oxidation are occurring together. And so let's look at this example of a redox reaction. So in this reaction, one species is being reduced, one species is being oxidized. Pause the video and see if you can find which species is being reduced and which one's being oxidized. So the easiest way to tell which species is being oxidized is to look at oxidation states. So let's look at the oxidation state of this I minus. Well, it's -1. For a halogen that is a single atom, the oxidation state is just going to be equal to this charge. Now let's look at the oxidation state on the right. And that's I2. Any neutral diatomic molecule where both atoms are of the same element, the oxidation state is going to be 0. Now let's look at this ClO3 and let's look at this Cl minus. So it's -1 here, but what is Cl over here? Is it also -1? Well, it actually isn't, and we need to be able to calculate these oxidation states. So chlorine, right? We don't know what its oxidation state is yet, so we're going to call it X. Now, what is the oxidation state of these 3 oxygens? Oxygen, unless it is in a peroxide, which I'll talk about later, always has an oxidation state of -2. But we have to take into account that there's 3 oxygens. So because there's 3 oxygens, we are going to put -6. Now the reason I've put X -6 here is because this is going to add up to something. And what it will add to is the charge on the molecule. So when we solve for X, we get 5, and that is +5. So chlorine has gone from +5 here to -1 in here. So has it been oxidized or reduced? Well, the answer is that the oxidation number has decreased, so it's been reduced. So the oxidizing agent, then, what is it? The oxidizing agent is the substance in the reaction which oxidizes the other thing. So this ClO3, it oxidizes the I minus and it becomes reduced. If something oxidizes something else, it becomes reduced. So this is our oxidizing agent. Our reducing agent then will be the I minus. Now, an interesting thing about this example is how do you balance a redox reaction? So let's go back to this reaction and see how we can balance it. So let's put I minus here. Let's put ClO3 minus here. Let's put I2 here plus H2O plus Cl minus. Let's remove the H2O, sorry. So on your Chemistry 12 tests, what you're likely going to see is something like this, right? This is not balanced. How do we balance it? So what you can do is you can split these into what we call half reactions. So let's start. I minus is going to become I2, right? The first thing we need to ask ourselves is this an oxidation or is it a reduction? Pause the video and see if we can come up with the answer. The answer to this question is that this is clearly an oxidation. And when we have oxidation, we're going to be using electrons to do that. So we know that it's an oxidation. Now, we need to, before we add electrons, we need to balance the I, right, the iodine. So I'm going to put 2I minus here. So 2I minus goes to I2. Now, how many electrons are there? So one thing about redox reactions is you need to balance the charges. So this is a -2 charge on this side. The reason is that we take this and we multiply it by this. And this is -1. This is a charge of 0. So if this is -2 here and this is 0 here, these charges are not equal. So we make them equal by adding 2 electrons. Because each electron has a -1 charge. 2 times -1. So this is an example of how we've balanced this first half reaction. Let's go ahead and balance the second one. Okay, so in this reaction, right, what we have is ClO3 to Cl minus. Now, this is a bit more complicated to balance, and I'm going to tell you why. So the chlorines are already balanced, one chlorine here, but there is an oxygen, O3. In redox reactions, we balance oxygen by adding water. So we're going to add 3 waters here. Now, in this reaction, we've now generated 6 hydrogens. So we balance hydrogens by adding H+. Then we need to balance the charges. How do we balance the charges? Well, we have a -1 charge here, and we have a +6 charge here. We know that this reaction is a reduction. So if it's a reduction, we need to add electrons to the right side. So by right side, I mean the correct side, not the right side of the equation. So which side do you think you're going to add the electrons to? Are you going to add them here, or are you going to add them here? The answer to this question is you're going to add them on the left. The reason is because if it's a reduction, the electrons are part of the reaction. They are almost like reactants. So how do we make +6 become -1? Sorry, I've made a small mistake. This was ClO3 minus. So this is actually +5, and we want to make this -1. So to get from +5 to -1, we need to add 6 electrons. So 6 electrons plus 6H plus ClO3 minus goes to Cl minus plus 3H2O. This is now balanced. But we have an overall reaction. So let's go and bring the other reaction here. Notice one small problem. We have 2 electrons here and we have 6 electrons here. So how do we fix this? We need to multiply this equation by 3. And the reason we need to multiply it by 3 is because we need to make this whole equation equal in the number of electrons to this one at the top. So we get 6E minus plus 6H plus ClO3 minus goes to Cl minus plus 3H2O. 6I minus goes to 3I2 plus 6E minus. We can cancel the electrons now, which is what we do in all cases. So we get ClO3 minus plus 6H plus 6I minus goes to 3I2 plus Cl minus plus 3H2O. This is the balanced redox equation, and what we are doing is we're adding this equation to this equation. If something appears on both sides, you can cancel it, provided that they both have a coefficient of 6. So that is how we find the balance redox equation. We split it into two half reactions, and we first balance it in this order. First, you balance atoms. So in this case, it was originally in this equation, right? We had I minus, right, and I2, so we put a 2 in front. Then you balance oxygen. Then you balance hydrogen, right? And so you balance oxygen by adding water. You balance hydrogen by adding H+. And then you balance the charges using electrons. So if you follow these steps, you'll be able to balance every equation you see. Let's try an example of calculating oxidation states. What's the oxidation state of sulfur in this? Pause the video and see if you can figure out the answer. So, let's start with our method. So we have S2O8, and there's a charge of 2 minus here. So, we're going to put the oxidation state of sulfur as 2x. Now remember I said about oxygen, it always has an oxidation state of -2, except in a peroxide. So we're going to put 2x minus 16 here, because there's 8 oxygens. And that's going to equal to the total charge, which is -2. So 2x is going to equal to -2 plus 16, which is going to be 14. And then x is going to equal to 7, and it'll be plus 7. So in this molecule, S2O8, the oxidation state of the sulfur is going to be plus 7. Now, let's move on to the next question. This was just a structure I drew for fun. Please ignore it. Okay. Let's start thinking about a common question, which is the following. Whoops. So, in this question, they are asking what is happening to the oxidation number of antimony in Sb2O3. So, the question is, how much does the oxidation number change? So let's start with our method. So we know that there's 2 antimonies, Sb2. So we'll do 2x minus 6 is going to equal to 0. And the reason it's 0 is because there's no charge on this. 2x equals 6. So x is going to equal 3. Now what about here? Well, the oxidation state here is 0 because it is just an atom. Any lone atom, it doesn't matter what it is, has an oxidation state of 0. So the oxidation state has decreased by 3. So the change in oxidation state is 3. And we can tell that it's a reduction, right? Because we've added those electrons and the oxidation state has decreased. So, let's talk about electrochemical cells as well. So far we've covered some of the major skills required by you in Chemistry 12, which is balancing redox reactions and finding oxidation states. But electrochemical cells are a major component of the course as well. So I'm going to draw an electrochemical cell, and I'm just going to go over what the different components do. Whilst you draw this along with me, you can start to label the components if you like. See if you can test your knowledge that way. Okay, so I'm going to talk about all these components in this cell. So let's start with the top. Let's start with what this is. Well, this is a voltmeter, and this voltmeter, and it's going to measure something that we know as the E cell, which will make more sense in a second. We have some electrodes here. One's made of zinc, one is made of lead. And they are in a solution. And the solution that they are in will be zinc nitrate and lead nitrate. Let's look at what's happening here. So we've connected these electrodes with wires. What do you think can flow through the wires? Pause the video and see if you can come up with an answer. Well, the answer is electrons. Electrons can pass through these wires. These are known as the electrodes. Now, the electrodes can be classed in two ways. We can have anodes and cathodes. At the anodes, we see oxidation. At the cathodes, we see reduction. So, let's start to think about what's happening at the anode and what's happening at the cathode. We have two potential species in each one. We have zinc metal, which is in the electrode, and we have Zn2+. Likewise, we have Pb and Pb2+. At the anode, we're going to get oxidation. So, which species do you think is going to be becoming oxidized? Lead or zinc? Well, the answer to this question is to do with what we call a reduction potential. And so in Chemistry 12, you're going to get this thing called a table of standard reduction potentials. And what this table contains is it contains the reduction potentials of all of these different elements, compounds, and you'll be able to find, if you get a question in Chemistry 12, the compound that you are dealing with. Now, what we have to consider is, what does the reduction potential tell us? What does the reduction potential tell us? Maybe you can answer this one. Well, the reduction potential tells us a very specific kind of information. It tells us if the reduction reaction is spontaneous or non-spontaneous. Now, the thing is with electrochemical cells, and I'll talk about electrolytic cells later, is that they can only operate spontaneous reactions. The reason for that is as follows. Electrochemical cells do not have an external power supply. They have a circuit, right? This is the circuit, but they don't have a power supply, which means they cannot drive non-spontaneous reactions. So what does spontaneity have to do with reduction potentials? if the reduction potential is positive, that means that the reaction will be spontaneous under standard conditions. Now, what are standard conditions? Well, the concentration here and here is 1 molar, and it's done at a specific temperature as well. And you can find that temperature online to do your own research. So, what we have to figure out is which reaction is spontaneous for the reduction reaction. So we're going to have two potential reactions. We have Pb 2 plus 2 electrons goes to Pb. We also have the following, which should be this one, which is Zn 2 plus 2 E minus goes to Zn. And that's solid. That's solid. Now, which of these reactions do you think is going to be spontaneous? Pause the video and see if you can come up with an answer. So I'm going to look at the table of reduction potentials. And this one is minus 0.13 volts. Now let's look at the one for zinc. So that would be Zn2 plus 2 electrons. This one's minus 0.76 volts. So one thing that you might be asking here is, well, they're both non-spontaneous, so how can they take place? Well, remember, there's also an oxidation reaction. So let's do that. We could have this, or we could have this. So these would be the oxidations. If we want to find the oxidation potential, right? Notice that this reaction is the reverse of this. So we can just flip the sign. Plus 0.13, plus 0.76. So what we have here is a reaction which is both spontaneous. So which one is it if they're both spontaneous? The answer is this one. And the reason is because the oxidation potential, not reduction potential, of zinc metal is higher than lead. So this reaction is going to be more favorable because this is higher. Now, if the zinc is being oxidized, the lead will be reduced. So the lead will be as follows. Pb2 plus 2 electrons goes to Pb. And that was minus 0.13 volts. So then how do we find if this overall reaction is going to be spontaneous or not? Because this is what's happening in the overall reaction. Zn, zinc, plus Pb2 plus is going to go to Zn2 plus Pb. This is a solid, this is a solid, and these are in solution. The ions will always be dissolved. So this is our overall reaction. Zinc is being oxidized, lead is being reduced, as we saw from this analysis we did. This overall reaction is spontaneous because what we can do is we can add this reduction potential to this oxidation. So 0.76, which is a positive, minus, right, 0.13. That is still a positive number. It's a pretty small number, but we get 0.63 volts positive, that is overall. That means that this reaction is spontaneous. Even though the reduction of lead is not spontaneous by itself, when we include the oxidation of zinc, the overall reaction is spontaneous. So, the overall reaction is spontaneous. That means it can take place in the electrochemical cell. So where is reduction going to happen? Reduction happens at the cathode. So in the cathode, right, if we go back to our diagram, this Pb2 plus is going to become Pb. And what it will do is it will deposit here. The cathode will then increase in mass. The anode is where oxidation is occurring, and zinc metal in the electrode is going into solution as zinc 2 plus. The mass here will come down. So, we are now in a very good stage, because we have now figured out the following. We know that the cell potential, which is what we just calculated, is 0.63 volts. We know that at the anode, we get Zn to Zn2 plus. We know at the cathode, we get Pb2 plus to Pb solid. And that's 2 electrons involved here. So, we know that this is oxidation. We know that this is reduction. Now, we have all the tools now to understand what's going on in the electrochemical cell. But there was this component here. What is this? This is the salt bridge. And now the salt bridge contains a cation, which is positive, and an anion. The cation, right, and the anion can flow through the salt bridge. And what it's used for is to prevent charge buildup. The anode is going to become positive. Positive anode, negative cathode. The cathode will become negative. And so the negative ion here, which is KNO3, will move to the anode, and the positive ion will move to the cathode. And this is to keep the cell running. Without the salt bridge, the reaction will stop. And the reason for that is because the cell would become what we call polarized. So this is a good introduction to oxidation and reduction, as well as electrochemical cells. If you do like this video or you have any feedback, please fill out the Google form and we can make changes to future video lectures. I would highly recommend that if you are using Hebden Chemistry 12 or another textbook, that you complete the chapter questions that are coming along with this lecture. Thank you.